All right, we'll get started. We have another talk on MPI, but I think a very different one, running MPI applications on the Toro Unikernel.
Exactly, yeah. So hello everyone, I'm Matthias. Here I'm going to talk about running MPI applications on Toro Unikernel. Usually speaking, a unikernel is a way to deploy a user application in a way that is closer to the hardware by trying to reduce the operating system interference. So in the overall, it should perform better than just deploying a user application by using a general purpose operating system. First, I would like to introduce myself. Well, I am passionate about operating system development and virtualization technologies. I had worked at Citrix, Digitech, Huawei, and I'm currently at Bates. And here I have my email and my GitHub profile if you want to know more about what I'm doing. So I'm going to start to present what is exactly a unikernel, and then I'm going to go to the details of what makes Toro special. And then I will show current implementation of the MPI standard on top of Toro, and I will finish with a benchmark that I'm trying to do to see if the current implementation is working as expected, or if there are things that could be improved. So maybe you are already familiar with this picture. This is more or less how a user application is deployed, either using a virtual machine or bare metal. So what we have is the operating system, the user application, and the two different modes, the Rin3, Rin0, which is the different modes in the x86 processor. So in general, what we have is that when a user application requires want to open a file, send a packet, or whatever, it's going to trigger a syscall, and then it's going to be a switch in which the processor is running from, which is user space to kernel space, so it's going to be processing at kernel space and come back, right? In general, when we see what we have inside the kernel is, we have different components, right? That, for example, we have the scheduler, the file system, different drivers, and so on. So in particular, what we have is a scheduler. A scheduler is going to choose what is the next process that's going to be executed. One of these processes, or several of them, is going to be your MPI application, for example. So if you deploy your MPI application by using a general purpose operating system, your application is going to compete with other processes in the system for sure. And also what you have in the scheduler is some policy, which is going to decide which is the next process to be deployed. Also, we have a component like the file system, and since we have a general purpose operating system, we're going to have several drivers for different file systems and different drivers and so on. So what some people observed was that there were too much generality in using a general purpose operating system for a single purpose application like can be a MPI. So some people come up with a new architecture. They propose what they call unikernel. You have some projects there like OSV, MirageOS, Unicrash, or NanoVMs. What they do is just take the user application and compile it within the kernel itself. So at the end, what you have is a single binary that is going to be deployed either by using a virtual machine or bare metal, right? So instead of, for example, having syscalls that we have in the case that we have a general purpose operating system and different modes of execution, in the case of a unikernel, we have simple calls, which are cheaper than using syscalls, for example. In general, the projects that I presented before all are conform to the POSIX standard, so it means that if you have any application written in C that conform to POSIX, you can theoretically compile with the unikernel without any modification of the user application. In reality, this does not happen, and most of the time, the POSIX that the unikernel implement is not complete, so you have to do some work to you cannot just take your application and compile it and generate something. It doesn't work out of the box in most of the cases, right? So in this context, what is Toro is also a unikernel. It's an application-oriented unikernel. And the idea of Toro is to offer an API which is dedicated, to efficiently deploy parallels application. In the case of Toro, it's not POSIX complaint. means that even if the name of the functions like sysopen, synclose, and so on is more or less the same names, the semantic of this function is slightly different. So I will not say that it's a POSIX complaint in that sense. And I will explain that later. So let's say that the three building blocks of the Toro unikernel are the memory per core, cooperative scheduler, and core-to-core communication based on virtio. Here I'm talking about the architecture of the unikernel. I'm not talking about yet the application of how we're going to build an application to conform to Toro, right? And I'm going to explain these 3 points. So first, what happened in the Toro unikernel is that we had memory dedicated per core. So at the beginning, what we do is just allocate split the whole memory in regions, and we assign these regions per core. And for the moment, the size of these regions is just proportional with the number of cores that we have. That makes that, for example, the memory allocator is quite simple. It doesn't require any communication because we have chunks of data. The allocator is, we have one allocator per core, which means that we don't require any synchronization in the kernel to allocate for one core. It's quite, we call it per CPU data, let's say. Yeah. So, for example, if you have a thread in a core 1 and we want to allocate memory, we're going always to get it from the same region, and that happens also if we are in the core 2, we are going to use in the region from region 2. And the idea is that by doing this, we can then leverage technologies like hypertransport or interquit path interconnect, in which we can say, well, this core is going to access this region of memory, and if you access other region, it's going to get a penalty to do it, right? So talking about the scheduler, what happened in Toro is that we only have thread. So we don't have process, means that all threads share the view of the memory. And we have mainly one API to create thread. It's called a begin thread. And it's the parameter that have to say in which core each thread is going to run. The scheduler is cooperative, which means that it is the thread that's going to call the scheduler to then choose another thread. And it's by relying on the API called thread switch. And most of the time, this is just invoked because we are going to be idle for a while, so we just call the scheduler. Or, for example, we're going to do some I/O. So the scheduler is also very simple. We have, again, per CPU data. So we have one queue per core, and the scheduler is simple going to choose the next thread that is ready and then schedule it. And this means that also we don't require any synchronization at the level of the kernel to schedule a thread. So it's like each core run independently one from another. Finally, I'm going to talk a bit about how we communicate cores. And basically what we have is one dedicated reception queue per core for any other core in the system. So we have one-to-one communication. It basically relies on 2 primitives, which is send and receive from, send to and receive from, and it's just by using the destination core and from where we want to get a packet, for example. These 2 primitives are the ingredients to then build more complicated APIs like MPIGather, MPIBcast, and MPIScatter. So these are the building blocks for those API, for example. So to implement this core-to-core communication, I was using virtio, so I was just following the specification. I will talk a little bit about this. I don't want to go too much into details, just to understand roughly how communication between core is done. As I said before, we have one reception queue for each core, for any other core in the system. So it means that, for example, if core 1 wants to get packets from core 2, we have a reception queue. And also if core 1 wants to send a packet to core 2, it's going to have a transmission queue. And the number of queues is going to be for sure different if you have 3 cores, for example, because the virt queues are dedicated. So basically how a virt queue works is made of 3 rings buffers. So the first ring buffer is a buffer which only contains descriptors to chunks of memory. The second buffer is a variable ring, and the third buffer is a user ring. Basically, what happens is the variable ring is the buffers that the core 1 are exposing to core 2. So the core 2 is if core 2 wants to send a packet to core 1, it's going to get a buffer from a variable ring, put the data, and then put it again in the user ring. This is basically how virtio works. Just that if you are familiar from virtio, in this case, for example, the consumer of a variable ring is the core 2. But if, for example, if you are in a hypervisor and you're implementing some virtio device, the consumer is not going to be the core 2, but it's going to be the device model, QEMU, for example. I don't know if you're familiar with that. But it's the same scheme. This allows that, for example, since we have one producer and one consumer, we can access to the virq without any synchronization. I mean, at least if we have only one consumer, right? So you don't require any lock, for example, to access to the virq. So yeah, I have already talked too much. I don't know how much time I have left. But I wanted to show some examples about the implementation. Maybe it's more fun than all the slides I should show. So what happened, how we deploy an application by using Toro? Well, we have the MPI application. This is a C application for the moment. And you compile it with a unit that's going just to link the application with some functions that are the implementation of the MPI, of the MPIs. That, for example, MPIGather, and so on is implemented in this level, in the MPI interface. And this unit is going to use some MPI from the unikernel. So at the end, what you're going to get is an ELF, a binary, that could be used to deploy your application, either as a virtual machine or a bare metal. So you don't have any operating system intermediary there. So you have only your application, the threads, and so on, but you don't have nothing else. So if you want to see how it is deployed, well, if you get the MPI application.c, what's going to happen is we're going to get the main and then instantiate it one for every core in the system as a thread. So to benchmark the current implementation, I'm not very familiar with the MPI where. I just coming from another domain, so I am not really familiar how I had to benchmark such implementation. And so I choose the OSU micro benchmarks. Maybe you know them, maybe not. And I just pick up one of them, like for example, MPI barrier, and I try to implement, which is quite simple. The benchmark itself is quite simple, so I decided to re-implement it. I could not take the benchmark as it is. I had to do some rework to make it work. And then my idea was to see how this behaved when I was deploying this as a single VM with many cores. The hardware that I use is this one. Since I'm not familiar with the high performance computing world, I'm not really sure if this is a hardware that you often use. It's quite a new Intel. You can get it in Equinix. The price is €4 the hour. Okay. So I launched the test and I tried to measure things. So I was just measuring the latency of this. And I was taking into account the max latency over 4, 8, 16, and 32 cores. I'm getting values in the order of the microseconds. And then I found this paper, which was also using this benchmark to measure their platform. And I was saying, well, in this paper, they were reporting in around 20 nanoseconds and 30 nanoseconds. Sorry, I made a mistake. This is microseconds, not nanoseconds, sorry. And in this platform. In any case, I will be very cautious about this graph because I was getting a lot of variation in the numbers. Most of the time, for example, I was trying in a machine with 32 cores, And then the BN has already 32 vCPUs, so you should not test in that sort of machine because one of the threads is going to compete with the others, with the main one of the host. So you should always test with less cores, less CPU cores than physical cores. And yeah, the idea is to continue doing this. I mean, improving the way I'm measuring this, and also trying maybe in different hardware. At the same time, I found a lot of bugs in the Unikernel by doing this. So for example, at the beginning, I only support more or less 4 cores. So I went from 4 to 32. Well, it was a number in a constant, but anyway, I found many bugs when I was doing this. So it is all, this is just a proof of concept and a work in progress. So you don't take it too serious, I'm trying to say. I don't want to jump into any conclusion from this. And but yeah, it was fun to do anyway. So that's all. I don't know if you have any questions.
So you said this runs on bare metal?
Sorry?
The Unikernel runs on bare metal?
Yeah, there are some.
How do you even install it? I mean, operating systems are kind of complicated, right?
Sorry?
How do you even install it on bare metal?
Can you say it again? I didn't get it.
How do you install it on bare metal?
How you solve
yeah,
it?
Do you have, like if I had this, how would I install it on bare metal? There's an installer or?
Installer, you mean?
Yeah.
No, you can just use, I don't know, some device to boot from, for example.
Well, so it's bootable?
Yeah, that's it. Yeah.
Okay.
Yeah. Well, yeah. You have many ways to do that. For example, you don't have to install it, for example. You can do it from a device that is removable, for example. You don't need to install it, I mean, whatever.
Any question? No?
Thank you.